Hi everyone. Today I want to talk a bit about complex numbers and imaginary numbers. Now these names came about historically and they're not really very good ones. Complex numbers are not particularly complex, and imaginary numbers, at least in the world of mathematics, are no less real than real numbers. Let's try and dispel some of the myths behind these concepts. So let's discover the maths of complex and imaginary numbers. A complex number is just a real number plus a real number times the square root of minus 1. In other words, a number of the form z equals a plus ib, where a and b are real and I is the imaginary unit, the square root of minus 1. The term IB is known as an imaginary number, or the imaginary part of the complex number a plus IB, and a is called the real part. So, just to be clear, an imaginary number isn't some bit of fantasy that we've just dreamed up. It's a very distinct, clearly defined thing in maths, a number whose square is negative. Every imaginary number can be written in the form IB, where b is a real number and I is the imaginary unit with the property that I squared equals minus 1. For example, the square root of minus 16 is an imaginary number, since the square root of minus 16 is equal to the square root of minus 1 times the square root of 16, which can be written as 4i. You can think of imaginary numbers as complex numbers in which the real part is 0. In the geometric representation of complex numbers on the complex plane, or an Argand diagram, which we're going to talk about in a minute, imaginary numbers lie on the y-axis. Another way to represent a complex number is as an ordered pair of real numbers AB, together with the operations AB plus CD equals A plus C, B plus D, and AB times CD equals AC minus BD, BC plus AD. Alternatively, complex numbers can be shown as points on an Argand diagram, a representation of the complex plane, in which the horizontal axis is the real number line and the vertical axis represents all possible purely imaginary numbers. Any point that appears on the complex plane off-axis has both real and imaginary parts. On an Argand diagram, a complex number can also be shown as a vector, or directed line segment, a line of a certain length with an arrow, extending from the origin, 0 plus 0i, to the number a plus bi. The absolute value or magnitude of a complex number z, thought of as a point on a plane, is its Euclidean distance from the origin, and is denoted as z between two vertical lines. This is always a non-negative real number. Algebraically, if z equals a plus ib, we can define the absolute value of z as the square root of a squared plus b squared. If the complex number z is written in polar coordinates, z equals r e to the I phi, then the absolute value of z equals r. Complex numbers are a natural extension of the real numbers and form what is called an algebraically closed field. Because of this, mathematicians sometimes consider the complex numbers to be more natural than the real numbers. All polynomial equations have solutions among the complex numbers, which is not true for the real numbers. Complex numbers are used in electrical engineering and other branches of physics as a convenient description for periodically varying signals. In an expression z equals r times e to the I phi, one may think of r as the amplitude and phi as the phase of a sine wave of given frequency. In special and general relativity theory, some formulas for the metric on spacetime become simpler if the time variable is taken to be imaginary. An imaginary operator, also called a J operator or I operator, is the part of a complex number that defines the magnitude of the part of the complex number at right angles to the real number part. We can understand it in this way. Consider a vector OP, where O is the origin of a set of Cartesian coordinates and P is the point AB. Multiplying OP by -1 produces a vector OP prime. That is, it will rotate OP through 180 degrees, such that OP prime equals minus OP. Now consider a number I, called the imaginary operator, such that multiplying OP by I produces OP double prime, a vector perpendicular to OP. Multiplying OP double prime by I will produce OP prime. Remember, we said that a graphical representation of the complex plane in which complex numbers are shown as points on a coordinate plane using the x-axis as the real axis and the y-axis as the imaginary axis is also known as an Argand diagram. It's named for the French amateur mathematician Jean-Robert Argand, 1768 to 1822, who described it in a paper in 1806. A similar method had been suggested 120 years earlier by John Wallis and had been developed extensively by Caspar Wessel. But Wessel's paper was published in Danish and wasn't circulated in the languages more common to mathematics at the time. In fact, it wasn't until 1895 that his paper came to the attention of the mathematical community, long after the name Argand diagram had stuck. Thanks for watching. Please subscribe if you haven't already, and I'll look forward to seeing you very soon to discover more maths.